Alright, ladies and gentlemen, this is our 2D Kinematics quiz review. Here I'm going over the 3 problems on your quiz review sheet. Here I'm only going to give you 2 problems on this quiz. 1 horizontal projectile and 1 angled projectile problem. And here you'll see that the quiz is modeled just like this. So if you're able to do these problems, the quiz shouldn't be as difficult as it seems. So we start with our horizontal projectile problem, where you take a running leap off a high diving platform. Are you crazy, guys? So here you're running at 2.8 meters per second and hit the water 2.6 seconds later. So my first question is for you guys to draw the trajectory path. So you don't exactly have to include the drawing of the high diving platform, but know that you're starting with a horizontal velocity of 2.8 meters per second, and your trajectory path should look something like this. It's not as accurate, but you get the point. Alright, that's part A. Now part B, I want you to state the initial horizontal velocity and initial vertical velocity, which means you don't have to do calculations here. You can just write the answer. So our initial horizontal velocity, Vx, is 2.8 meters per second. And your initial vertical velocity is 0 meters per second. Now keep in mind, we are starting here with only a horizontal velocity. There's no vertical arrows going up or down, so there's no initial vertical velocity to start off. Now before you even start calculating, I'm going to start filling out our T-chart off to the side. Some of you might not be a fan of writing down T-charts just because it's a lot of work. It might be a lot of work, but at least it's an organized way to keep track of your variables. So in the x direction, we only have Vx, dx, and that's it. On the y section, we have VIY, we have AY, we're also going to need dy, and time. Remember that time is the same for both. Alright, now we can start moving on to part C. How high was the platform? So when you're thinking to yourself how high, that's a vertical distance, so we're solving for dy. So looking back into our T-chart, we already have 2.8 meters per second for Vx. We don't know what this is, dx. VIY is 0 meters per second, and acceleration vertically is 9.81 meters per second squared. And dy is what we're looking for. We also don't know t total. Okay. Actually, t total they already gave us. Oopsies. T total in the problem is 2.6 seconds. Sorry. So when looking for dy, we look in our vertical side of the table, and we're seeing which kind of equation we can use to solve for dy. We got VIY, we got AY, and we got t total. That means you're going to use your 3 kinematic equations to solve for it. So off to this side, I'm going to write the 4 different equations we can use. V equals d over t. Vf equals Vi plus At. D equals Vit plus 1/2 At squared. And Vf squared equals Vi squared plus 2Ad. So, given we're in the y direction, we can only use 3 of the latter equations. So we're going to use something with distance, initial velocity, acceleration, and time, and that's our d equals Vit plus 1/2 At squared. You know, earlier today I was having breakfast at IHOP, and some kid was listening to the wheels on the bus go round and round for so long. I got the song stuck in my head. And you know what? After listening carefully to the lyrics, I realized you can make the song sound as crazy as possible. And from the sound of it, it sounds like a carjacking. Not a carjacking, a bus jacking. So think about it. The wheels on the bus go round and round. The horn on the bus goes beep, beep, beep. The people on the bus go up and down. The baby on the bus goes wah, wah, wah. Sounds like a crazy bus. Sounds like it's getting jacked by someone. Honestly. Alright. So if you notice, anything times 0 goes away. So you're left with this part. Most of you can do the math straight away, but in case, I've seen a lot of mistakes here. Remember that anything times 0 goes away, so you're left with this, and all you need to do is multiply and divide here. Okay? Oh, actually there's no division, you can just multiply straight away. So you should get, so your platform, dy, should be 33.16 meters high. That's your answer for part C. Now part D, how far from the edge? So it's asking for dx. So looking at your 4 equations, v equals d over t is the only equation you can use in the x direction, so we're going to use that. Now keep in mind, anything in the direction, you use those values, so 2.8 meters per second equals d over our t total is 2.6 seconds. Multiply those two values together to get your dx, and you get 7.28 meters. Alright, now part E. Part E wants you to state what's the horizontal velocity right before you hit the water. So let's keep in mind here, horizontal motion is constant, so it stays a constant 2.8 meters per second, your horizontal velocity. In the vertical direction, however, because of gravity, you're accelerating, getting faster, so you accelerate from 0, getting faster and faster and faster vertically, which is why objects and projectiles eventually come back down because of gravity. If there is no acceleration at all in x or y, it will just keep going straight in the air, horizontally. Nothing to bring it down. That's why it has this curved path going downward. It's a mix of both horizontal and vertical. So we're just focusing on horizontal, it stays constant. So if we start with 2.8, we should end with also 2.8 meters per second. Because it stays constant. Alright, number 2. Same spiel. This time you accidentally threw your keys off a cliff. Again, you're crazy. Alright, so again, draw the trajectory path, same thing. Let's see if I could draw it better. Well, it's not even that much better. Alright. Okay, so once again, let's state our values. We have a 64-meter high cliff, so that's now our dy. AY is still 9.81 meters per second squared. Our initial was 0. This one now is 8 meters per second. Alright, so we got part A. Part B wants us to state initial horizontal velocity. That's 8 meters per second. VIY is 0 meters per second. Part C wants us to find the air time, so we're looking for T total. Again, we don't have information in the X, so we gotta look to information in the Y. And we gotta find it. It's still using D equals VIT plus 1/2 AT squared. You just plug in chug to find T. So don't hesitate to slow it down. Okay, solve for T, divide, and then take the square root to solve for T. And so T total should now equal 3.61 seconds. That's your air time. Alright, now part D. How far from the base of the cliff? Same spiel. Okay, V equals D over T. So 8 meters per second equals D over 3.61 seconds. D is equal to 28.9 meters. Alright, now E is asking for what happens to the horizontal velocity. It stays constant. Because we don't have air resistance, no friction in the x direction, so it stays constant at 8 meters per second. That's it. Now we get a whole page devoted to just one angle projectile problem. But once again, we still do our T-chart, but it's going to look different. Still got VI, Y, we got VFY, AY, DY, and T half. We got Vx, dx, and T total. So again, time is still a factor to combine both x and y and bridge them together. But the time you solve for in either direction is slightly different. You can only solve for the time halfway through in the y direction, but you could easily double that to get you the total time in the x direction. Okay, now, in a football game, a quarterback throws a ball to a receiver. The quarterback takes the hike from the center. 3 seconds later, he passes the ball with a velocity of 20 meters per second at a 30-degree angle with the ground. The ball is caught at the same height it was thrown from. So that 3 seconds later is kind of irrelevant. But what we do need to know, is our velocity and the angle. 20 meters per second and a 30-degree angle. Alright. And it's caught from the same height it was thrown from, so this is a symmetrical projectile. So that means when you throw the ball, kind of symmetrical. Get the same point. Alright. Part A, find the vertical and horizontal components of the ball's velocity. So that means we have to resort to these guys. Vx, Vy, okay, V cosine theta, V sine theta. Alright, so our velocity here is 20 meters per second times the cosine of 30 degrees. 20 meters per second times the sine of 30 degrees. Sine 30, you should remember for some of you guys who've taken trig, is 1/2. This one is 10 meters per second. This one is about, I'm going to say about 16, 17-ish offhand. Correct me if I'm wrong, it could be about 16, 17-ish, so cosine of 30. Do this. 30 cosine times 20. 17.32. Not bad. Alright. Now, part B. Oh, before we even go to part B, let's put these in our table. So this right now, Vx is 17.32 meters per second, and Viy, because you throw it initially with this speed, vertically, 10 meters per second. Alright, how high did the ball travel? Before we even do that, we need to fill in the rest of our values here. So remember, when you throw something up into the air, it's going to reach a peak right here. And at that peak, in the vertical direction, it doesn't have a speed. The ball reaches 0 velocity at the peak. Because in order to change directions and come back down, it needs to stop. And because it's going upward, working against gravity, we're going to make it a negative 9.81 meters per second squared to show that it's slowing down. Alright? And I believe that's all we have right now. Alright, how high did the ball travel? Alright, we're looking for dy, which means we look at our equations. This is the equation we can use. Plug and chug. Keep in mind, we're using stuff in the y direction. We're looking for how high, so that's a vertical direction. We use information in the y. So this math can be kind of difficult here for people, so I'm going to do it in a different color. Alright, now you don't combine the 100 and the 19.62. Remember, they're two separate terms because one of them has the variable. So you bring the 100 to the other side. Divide by 19.62, and you should get that D is equal to 5.1 meters. That's not that high. Okay. Now part C, how much time did the ball spend in the air? So we're looking for total time, but we can't figure out total time in our x direction. That means we have to go to the y direction to find half the time to the peak, double it to get the total time across. Alright, now let's pick a different color. Let's put C. Alright, we can use this equation. I like this equation much better. You get 1.02 seconds for its halftime. Total time, now you double that, and you get 2.04 seconds. 2.04 seconds, so it's 1.02 seconds here, 2.04 seconds here. Alright, now we can move on to the next part, part D. How far down the field? We're looking for dx now. Now we could go use v equals d over t. Now we're in the x direction. We have vx and t total to solve for d. So you could do 17.32 meters per second equals d over 2.04 seconds. So d is now equal to, when you multiply both numbers together, 2.04 times 17.32. You get 35.33 meters. So if you convert that to yards, that's a little closer to 40 yards for a pass. Alright, part E. What speed did the ball hit the ground with? Again, this is symmetrical, so if you launch the ball 20 meters per second, that means it's coming back down with that same speed, just in the opposite direction, also 20 meters per second. It didn't specify vertically or horizontally if it wants the final velocity. So we're going to take it as the general velocity as it hits the ground with. So for part E, if it starts 20, it should also finish 20 meters per second, because this is a symmetrical motion. Part F. Let me just write down the reasoning. Part F. What happens to the vertical velocity of the ball as it travels through the air? It slows down to 0 at peak, then accelerates back down. So remember, when the ball is thrown up into the air, it slows down because of gravity acting opposite direction till it reaches the peak, and then it speeds up, coming back down. Now, part G. How should the launch angle change to allow for greater airtime? So remember, we are starting at a 30-degree angle. This is a pretty horizontal angle, more horizontal than vertical. If you increase it closer to 90, that's when you're going to get more airtime because it allows for more vertical velocity, more height. So the more vertical height you get, the more airtime you have. Now for range, if you want to increase the range, that means the horizontal distance, this is reliant on both airtime and horizontal velocity. So you need to have a lot of horizontal velocity, which means you need a lower angle, but you also need a lot of airtime to get it to travel far with enough time in the air. So that means you need the best of both 0 and 90 degrees. So what's the best angle between that? That's 45 degrees. Right in the middle has the best of both vertical and horizontal aspects. So doing that, you should be closer to 45 degrees. Alright? And that brings us to the end of this review video. Alright? So remember some of the key points here, especially on the launch angle. More vertical height, more airtime, which means you need to go closer to 90. For range, you need to get the best of both vertical and horizontal aspects. You need to go 45 degrees. Okay, so review a lot of some of these basic concepts. A lot of these easier components of these questions are conceptual questions, which you'll definitely need to move forward in the problem-solving components of these questions. Alright, so I hope this was helpful. Take care, guys. Don't study too hard. Bye!